This video is brought to you by mywayteaching.com.
So here the example 3. A cyclist comes to a skidding stop in 10 meters. During this process, the force on the cycle due to the road is 200 Newton. Okay, and it is directly opposed to the motion. So now we should find how much work does the road do on the cycle in the first part, and in the second part how much work does the cycle do on the road. Here they have given the displacement as 10 meter and the force that is given as 200 Newton, isn't it? And it is directly opposed to the motion. So in the first part, that is work done on the cycle by the road, is nothing but the work done by the frictional force on the cycle due to the road, isn't it? That is what the stopping force is, nothing but the frictional force. So the stopping force and the displacement, they make an angle of 180 degree. So we can find out the work done by the road, that is given by WR is equal to F d cos theta, and here they have given the value of F as 200, the displacement that is 10 meter, and the theta value is 180 degree, that is pi. So we get the value, that is 200 into 10, and cos 180 is minus 1, so we get minus 2000 joules. So it is this negative work that brings the cycle to a halt in accordance with work energy theorem. So moving to the second part, that is how much work does the cycle do on the road. So now let us find that part. See, from Newton's third law, an equal and opposite force acts on the road due to the cycle, isn't it? So its magnitude is 200 Newton. However, the road undergoes no displacement, thus work done by cycle on the road is zero. Since the road does not, even though a force of 200 Newton is applied, the work done by the road or the work done by the cycle on the road is zero, because road does not undergo any displacement. So here the work done by cycle on the road is zero. Okay. So now let us study in the next part the concept of kinetic energy. Okay. So we already studied about the equation of kinetic energy. If an object of mass m has a velocity v, then its kinetic energy k is given by half mv square, isn't it? And this kinetic energy is a scalar quantity. It is a scalar quantity. Okay. And the kinetic energy of an object is a measure of the work an object can do by the virtue of its motion. It is just a measure of the object, the work which is done by the object by the virtue of its motion. See, and this notion has been intuitively known for a longer time. See, the kinetic energy of a fast flowing stream has been used to grind corn. Sailing ships employ the kinetic energy of the wind. So these are all a few examples. So here we can see the kinetic energy of various objects in the table. See, the car, which is having a mass of 2000 kg, a speed of 25 meter per second, and the energy, that is the kinetic energy, 6.3 into 10 raised to 5 joules. Okay. Similarly, the running athlete of mass 70 kg the speed is 10 meter per second and the kinetic energy of 3.5 into 10 raised to 3. And bullet stone drop from 10 meter, raindrop at terminal speed, and air molecule. So of all these different objects given the mass, speed as well as kinetic energy. Okay. So now let us study one more simple example. See, in the ballistics demonstration, a police officer fires a bullet of mass 50 gram with a speed of 200 meter per second on soft plywood of thickness 2 centimeter. So, a police officer fires a bullet of mass 50 gram with a speed of 200 meter per second on soft plywood of thickness 2 centimeter. Okay, so the bullet emerges with only 10% of its initial kinetic energy. So what is the emergent speed of the bullet? See, it will emerge only with the 10% of its initial kinetic energy. So what is the emergent speed of the bullet? That is the question. See, the initial kinetic energy of the bullet is given by, okay, the initial kinetic energy of the bullet. So we know that formula, isn't it? That is given by 1 by 2 mv square. Okay, that is given by 1000 joules. Okay, it has a final kinetic energy which is of 10% of the initial kinetic energy. So that final kinetic energy is given by, so here how we got this 1000 joules? Here they have given the mass that is given by 50 gram and the speed is 200 meter per second. So using those two we'll get the initial kinetic energy. Okay. And the final kinetic energy is 10% of the initial kinetic energy. Isn't it? So that is given by 0.1, that is 10% of the initial kinetic energy, that is 100 joules. Okay, and if Vf is the emergent speed of the bullet, okay, Vf is the emergent speed, then we can write it as the final kinetic energy half mvf square, that is given by 100 joules, isn't it? And we know the value of what mass, that is 50 grams. If you write in terms of kg, that is 0.05. So vf square is equal to 100. So vf is equal to 200 divided by 0.05 square root. So that value is given by 63.2 meter per second. So the speed is reduced by approximately 68% but not 90%. Okay na? So here in this particular case we'll first find out the initial kinetic energy, so which is very important. So that is given by 1000 joules, because that is half mv square, where m is 50 grams, that is given by 50 into 10 raised to minus 3, and the velocity or the speed we can say that is given by 200. So 200 So this one we'll get it as, yes, 1000 joules. And then we found out final kinetic energy and the emergent speed of the bullet. So now let us see the next important part of this particular chapter. That is nothing but work done by a variable force. Okay. See, a constant force is very rare. It is the variable force which is commonly encountered. So wherever we go, we see variable forces only. So we can see the plot of varying force in one dimension. So in the figure you can see here the plot of varying force in one dimension. See, if the displacement delta x is small, we can take the force f of x as approximately constant, and the work done is, then we can write that work done as delta w is equal to f of x into delta x, only in case if the displacement, that is delta x is very small. Okay, in that particular case we can take delta w is equal to f of x into delta x. Okay, so we can see in this particular figure the expression. See, adding successive rectangular areas of this figure, you can see, right? There are so many rectangular areas. So, adding all these successful rectangular areas, we get the total work done. So, that total work done is given by W. That is given by sigma x, yes, sigma xi to xf. Initial range is xi and the final range is xf. Okay, xi to xf, f of x delta x. This is the total work. Okay, so where the summation is from the initial position x of I to the final position x of f. You can see in this diagram the initial position is given by x of I and the final position is given by x of f. See, if the displacements are allowed to approach 0, then the number of terms in the sum increases without limit. Okay, so but the sum approaches a definite value which is equal to the area under curve. So when displacement reaches 0, the whole summation term, that is w is equal to delta, no, the w is equal to sigma xi to xf f of x delta x, what we have written here. So this will, it will provide the area under the curve. So we can write that as W is equal to limit as delta x tends to 0, sigma xi to xf f of x delta x. Okay, so this is the equation. So we can write in terms of integration also, that is from xi to xf f of x dx. Okay, so where limit stands for the limit of the sum when delta x tends to 0. Thus, for a varying force, the work done can be expressed as a definite integral of force over the displacement. Okay, here we have expressed in terms of integral over the displacement xi to xf, isn't it? Yes. So we can consider one more figure. See, the shaded rectangle, it represents the work done by the varying force f of x over the small displacement delta x, where delta w is given by what? F of x delta x. Okay. So, and that this is given in the figure that we saw just now here. Okay. And in this particular figure, we can see adding the areas of all the rectangles, we find that for as delta x tends to 0, it gives the area under the curve which is exactly equal to the work done by f of x that is shown in this particular graph. Okay.